Now we'll consider the philosophers after the time of Plato and Aristotle, the later Greek philosophers. Euclid arrived in Alexandria about 10 years after its founding, during the reign of Ptolemy I. Euclid was the founder of geometry, obviously a hugely influential mathematician, because his Elements is a collection of all the mathematics that was known to humans at the time of the ancient Greeks. It's the oldest comprehensive deductive treatment of mathematics, and it was still used in schools until the late 19th century. He used the idea of axioms and deductive proofs, the rules of deductive logic having been worked out by Aristotle some century before. He used illustrations and diagrams in his proofs, which made them legible and understandable to people, even those who could not read. He wasn't an astronomer, but the importance of the elements can be hardly overstated because it's the basis of all science. In this picture, the philosophers from the late part of the Renaissance, we see Euclid, Ptolemy, and their students. Aristarchus is a major figure. He's the first proponent of a heliocentric universe, almost 2 millennia before Copernicus. His only surviving work is called On the Sizes and Distances of the Sun and the Moon. In his book, The Sand Reckoner, Archimedes tells us about Aristarchus's cosmology, and that's really the only reason we know about it, because so little of Aristarchus's writings survive. In the cosmology of Aristarchus, the fixed stars in the sun are stationary, and the Earth moves in a circular path about the sun. The fixed stars do not show a seasonal variation in their brightness and angles, a phenomenon called parallax, since they are at such a great distance. Aristarchus invented improvements to the sundial, and he studied in Alexandria, which was rapidly becoming the intellectual center of the world. Here's an example of his logical and geometric thinking. He was aware that the Earth, when it casts a shadow and the moon passes through its shadow, the moon occupies a small portion of the shadow. This was important because it told people at the time of the ancient Greeks that the moon was smaller than the Earth, and by how much. Also, since the Earth's shadow cast a curved arc across the moon, that told people that the Earth was a sphere, because only a sphere held at all different orientations will cast a circular shadow. So this was a geometric basis for believing that the Earth was a sphere, for people who may never have traveled very far in their lives. He also used the geometry seen on the right here, the angle of the sun and the moon at quarter phase, when the moon is half illuminated, to measure the small angle on the right side of the diagram. And from that geometry and the relative Earth-Moon distance, he could deduce that the sun was both much further away and much bigger than either the Earth or the moon. So to Aristarchus, it made no sense for the big thing to go around the smaller thing. It made much more sense for the Earth to go around the sun. He knew that the sun was larger than both the moon and the Earth and very far away. Now, the actual angles he measured and the actual amount by which he estimated these scales were wrong, but the principle was correct. And this was the first sun-centered or heliocentric cosmology, the correct cosmology. Sun-centered cosmology is more consistent with what we see because it provides a natural explanation, as we've already seen, for the retrograde motion of Mars. The problem is that as the Earth moves in its orbit of the sun, nearby stars should appear to shift relative to farther away stars, or their brightnesses should change as we move closer to a star in one part of the sky in one part of the cycle of the Earth, and further in another part 6 months later. The fact that we cannot see the stars change their relative positions or their brightness through the year means that this effect must be so small we can't see it, which means that the stars must be incredibly far away. So for his model, Aristarchus was forced to hypothesize a very, very large universe with the stars enormously distant compared to the distance between the Earth and the Sun. This is what makes it audacious. Eratosthenes, also around this time frame, provided not only the geometric argument for a spherical Earth, but actually a way to measure its size. He noted that at a particular time of the year, when the sun casts to the bottom of a deep well, in one place, it casts a shadow with a certain angle at another place. And using similar triangles as in this diagram, you can measure the distance between 2 points on the Earth's surface as a fraction of the total circumference. Here's the math of how they did it. And using this measurement, they actually got a number that was amazingly close to the modern number, within 5%. I think this is lucky because their measurement of the stadia, or the distance on the Earth's surface, was actually quite crude. But this is why an average educated Greek at the time of Aristotle and later would know, without questioning it, that the Earth was spherical and about how large the Earth was. Again, audacious knowledge for people who in their lifetimes would likely not travel more than 50 or 100 miles. The next figure, a culminating figure in this period, is Ptolemy. He put together the geocentric model of antiquity, the Ptolemaic model, and it was sufficiently accurate to remain in use for 1,500 years. But as mentioned, because of the non-uniform motion of the planets, it needed offset spheres and multiple spheres to explain the motion of a small number of objects. Ptolemy's work was written into a collection of books that collectively were called the Almagest, Arab for the greatest compilation. And he codified the Earth-centered, or geocentric cosmology, as a set of nested, concentric, crystalline spheres. He also made a catalog of stars in 48 constellations taken from Hipparchus, and that's the first star catalog we have in history. So we can see in antiquity there are two threads of thought. There's mainstream or orthodox cosmology, and a question that arises is, why did it last so long? This is the Earth-centered cosmology, where the Earth is stationary and spherical, but is at the center of the universe. The geocentric model, as we have seen, was driven by Aristotle's philosophy and his enormous intellectual influence. It does explain the data at some level, and it was comfortable because it's anthropocentric. It puts humans at the center. Eventually, as we'll see, it becomes Catholic Church dogma. Meanwhile, the dissenting model, the model of Democritus, Epicurus, and Aristarchus, involves atoms, tiny particles that are unseen, and a sun-centered cosmology where the Earth is in motion, yet none is felt. This is very close to the modern worldview, and it was forgotten or suppressed, depending on how you want to look at it, for 1,400 years. The real answer is that new tools, new evidence, new data was required to resolve this. And that's the end of this topic.